just want to start by thanking Kathy and Hadeen and Laura and Dawn for this opportunity to talk about some of the things I've been working on recently. So my background is in behavioral neuroendocrinology, and for the last 25 years or so, I've been studying hormones and behavior in non-human animal models. And a few years ago, I became really interested in how sex differences are tested for and interpreted and reported in all research, including research on humans. And today I'm going to focus on some of those things that I've been thinking about, the big one being, what do we mean when we say sex difference? And when we find one, what does that buy us? And first, we really need to think about what we mean by sex. How is sex defined and operationalized? Because it turns out that this is not straightforward. And I'm not just talking about humans and the entanglement with gender. Even people who work with non-human animals and cells grapple with this question, even if they may not even realize that they're grappling. And then in order to find a difference between the sexes, we have to compare them with each other, of course, by definition. But again, it turns out that that's not always so easy. And you'd be surprised by how often a sex difference is reported without the sexes even being compared at all. And then finally, let's say we do compare the sexes and we find a difference. What does that difference look like? How do we interpret it? And how do we use that knowledge toward a higher purpose? Now, I'm not going to answer any of these questions today, certainly. These are questions that I just want to pose to point out that the answers are not as straightforward as they might seem on the surface. And that's really important because we've been told that including both sexes in our research is critical for rigor and transparency and reproducibility. So let me give a little bit of context about rigor and transparency and what brought us to where we are today. And this story is going to be familiar to probably a lot of you. So before 1993, most NIH-funded clinical trials were conducted on men. So there was this culture of assuming that whatever drug treatment works well in men will also work well in women. In other words, NIH was treating men as the default human. But with this Revitalization Act, now by law, all NIH-funded clinical trials have to include women. And these are data from Beery and Zucker, about a decade ago, who showed that for research on humans, the sex disparity greatly improved after 1993. So this is the percentage of articles that they found in the literature. And you can see that between 1989 and 1999, there's this big increase in the percentage of articles that report that they've used both sexes. And I want to stop here just to mention that in this talk, I'm going to be referring to males and females sometimes as, quote, both sexes, largely because in the studies that I'm going to be talking about, like the ones summarized here, no sexes or genders besides males and females are usually considered. So this big increase is, of course, a huge improvement. And now women make up slightly more than half of participants in NIH-funded clinical research. But for research on non-human animals, which is what NIH calls preclinical research, there was no discernible improvement. So you can see that even after 1993, research on males only was still dominating. And so in response to this and a lot of similar reports, NIH implemented SABV, or sex as a biological variable, in 2016, and I'm sure you're all familiar with this, but it requires researchers to consider sex not only at the stage of clinical trials, but at every level, starting with basic science on cells and animal tissues. Now, the goal of SABV is to increase not only inclusivity, but also rigor. So it was rolled out as part of a much larger initiative on rigor and transparency. And one of the things that I've been looking at is the extent to which including both sexes actually does increase rigor, which I'm defining as lowering the risk that we're going to draw the wrong conclusions from our data. And I need to give a shout out to Janet Rich Edwards and her co-authors, all of whom are here at the Brigham. This is a paper from Endocrine Reviews in 2018. And they argue that without careful methodology, the pursuit of sex and gender difference research as a poorly considered mandate will result in a literature of contradiction, which is a really fantastic way to put it. Unless we do this carefully, we're in danger of a crisis in rigor and reproducibility, not necessarily an improvement. Excuse me. Okay, so following in the footsteps of Janet and her colleagues, let's consider these questions, starting with what do we mean by sex? So sex is a slippery concept in all contexts, including clinical and preclinical health research. An Israeli scientist named Daphne Joel has pointed out that for most of us, sex is defined by the alignment of three different things that all start with G. So she calls this 3G sex. Genes, in other words, what sex chromosomes you have, gonads, that is which gametes you make, and genitalia. And for many individuals, these three things align, which makes things pretty easy. But sometimes they don't align. And so sex becomes harder to operationalize. Which one do we pick? And then it gets even more complicated if we're studying things like disembodied cells in culture, right? So it's been said that every cell has a sex, which of course refers to the genetic component. But what do those genes mean to the cell if the cells are cultured in media, for example, containing steroid hormones and other things that might interact in different ways with genes? Are sex differences, particularly in humans, really able to be modeled in this context, and in what capacity? And the concept of hormones comes up all the time, particularly estradiol and testosterone, which I've shown here. And I'm working on a project right now looking at how SABV is implemented at Emory. And I'm interviewing Emory researchers about their work. And one of the things that has really struck me is how slippery their definitions of sex are and how important hormones are in that definition. So they'll be saying, oh, we sex our mice using visual inspection, or sometimes we genotype them, but then suddenly the language, like mid-sentence, turns to hormones. So the language that they're using around sex is suddenly about hormones. And I realized that they're using hormones as a proxy for how they operationalize sex, even though they might not even measure the hormones, but it's the hormones that they're really thinking is the independent variable in their study, and it's not even one of the 3Gs. And then of course, if we're studying humans, there's a complex array of other factors that co-vary with sex, gender, gendered professions, sex differences in occupational exposures, sex differences in access to healthcare, and all of this is coming straight from Janet's article. All of these can cause apparent sex differences, but those differences are nearly always attributed to, quote, biology, right, when interpreted by researchers and by the media. Now, when we say that we're including sex as a biological variable, and what we're actually doing is we're talking about a lot of different things. This has been called sex contextualism, and Sarah Richardson just published a series of articles about this, where she argues that changing your definition of sex depending on your study is not a bad thing. It's something that you have to do in order to be precise and rigorous with your science. You first have to decide what you mean by sex, and then design your study and report your results accordingly. So I'm going to leave this first question for a moment and move on, but I'm going to come back to it at the end. So next, if we're going to find a sex difference, we have to compare the sexes with each other somehow. But I want to point out that NIH does not actually require comparing the sexes. So this is the guidance to reviewers on how to evaluate whether SABV has been addressed in grant proposals. And the gist of it is that if your study is not intended to test for sex differences, in other words, that's really not what your lab is interested in, all you have to do is include both sexes in your study, and then report your data disaggregated by sex. You don't need to test for sex differences. And this is really interesting to me. So I recently started looking at how often the sexes are being compared in SABV compliant research. And to do this, I used a data set that was previously published by Wojtowicz et al. A couple of years ago. And they were interested in the extent to which males and females are being included to begin with. And this is a river plot that I made of their results. Now, what they did was they analyzed 720 papers, all published in 2019, in 9 biological disciplines. And those disciplines were things like behavior, physiology, neuroscience, reproduction, and so on. And they looked at human and non-human animal research. And what they found was only a minority of studies used both sexes, slightly less than half. And then they also looked at whether the sexes were pooled or whether they were analyzed by sex. And their definition of analyzed by sex was that the data were disaggregated by sex or that sex was included in the statistical model. And you can see that in their analysis, the majority of articles pooled the sexes instead of analyzed by sex. Now, I myself was really interested in this group of papers where both sexes were included and the data were analyzed by sex. I wanted to know how often the sexes were compared with each other in these papers, and if so, how often sex differences were found. So working with a graduate student, Yesenia Garcia Cifuentes, I asked these questions. When the sexes were actually compared versus being analyzed separately, how often were sex differences found? And then when a sex difference was reported, what kind of evidence was offered for that difference? So we focused on these 147 papers and categorized them further into more categories. We looked at whether the papers compared the sexes or not, and of those, whether they found a difference or not, and then of those, whether they made a big deal out of the difference. And what I mean by that is the difference was mentioned either in the title of the paper or the abstract. So that's how we defined major finding versus minor finding. And what we found was that when both sexes are included, the sexes were compared most of the time. And a sex difference was found more than half the time. And when it was found, it was treated as a major finding about half the time. So I think that we can rest assured that when researchers comply with SABV, meaning that they disaggregate their data, they are very likely to test for and report a sex difference. So on to our next goal, which was to look at the type of evidence used to support a finding of a sex difference. And we focused on studies with a particular design that I'm going to go over here. Now, most studies that are affected by SABV are going to have a type of design where before 2016, there might have been only one sex of mice, for example, either in a treated group or in a control group. But now for researchers complying with SABV, we have two sexes for a total of 4 groups. Now, you might not actually double your sample size, and I'm going to come back to that. But we have 2 control groups and 2 treated groups. And this is called a 2x2 factorial design, where sex is one factor and then something else like a treatment is the other factor. So now let's look at some hypothetical results. Now, I borrowed this figure from Annika Gompers off the genderscilab.org website, which I highly recommend. And let's say that whatever you're measuring is over here on the y-axis. And here are your data from your 2 female groups, and here are your 2 male groups. And a lot of people, particularly if they are really trying to follow the NIH guidelines to analyze males and females separately, they might do a t-test or some other comparison of means within the females and then another separate test within the males to look for effects of the treatment within each sex. So let's say in this example that we do this, and for females, there's a significant effect of the treatment. So our p-value is below our alpha of 0.05. But then let's say that our test in males is we get a p-value of above 0.05. So what do we conclude here? Is this a sex-specific effect, meaning that the treatment had an effect in females, but not in males? Well, the answer to that question is that we haven't tested here whether the males and females had a different response to the treatment, because we haven't compared the sexes with each other at all. We tested for effects of treatment within each sex. So to be able to conclude there's a sex-specific effect of treatment, we'd have to look for a statistical interaction between sex and treatment. In other words, we need to put sex as a factor into our statistical model and analyze the data altogether in that model. Now, not doing that, in other words, just eyeballing these 2 p-values and concluding a difference, is actually a very common statistical error. It's called the DINS error, or the difference in nominal significance error. And there's been a ton of papers written about it. And my favorite among these titles is this one by Gelman and Stern. The difference between significant and not significant is not itself statistically significant. That was published back in 2006. Now, a lot of us have probably done this, and I only found out that this error was a thing a few years ago, and I recently went back to look over my own published papers, and there it was, plain as day. It's an extremely easy error to make. But the gist of it is that you can't use a p-value of above alpha, above 0.05, to accept the null. In other words, to claim there's no effect in one sex. That's not how null hypothesis significance testing works, and it's not how we're supposed to interpret p-values. To test whether the sexes respond differently to treatment, we have to test for an interaction between sex and treatment. So coming back to our study, we wanted to know how often authors actually tested for interactions versus making the DINS error. And of the studies we looked at, a majority did have a factorial design with sex as a factor. That's what's shown here in purple. And the gray studies up here, these were just like comparing a group of females and a group of males without these other factors. And so that's not a factorial design, and those were not considered further here. But of the ones with a factorial design, the authors tested for interactions between treatment and sex only 29% of the time. And when they didn't test for interactions, the most common statistical approach was to make the DINS error, which is to test for effects of treatment within each sex. One thing we also saw a lot of was testing for an effect of sex within the treated groups, so ignoring the control groups completely, which is also not what you want to be doing. But the scariest thing to me with this study was that when the authors failed to test for a sex-specific effect, they reported one 88% of the time, compared with when authors actually tested for a sex-specific effect, they reported one only 63% of the time. And this was actually a statistically significant difference. So when authors who failed to test for sex-specific effects, but authors who failed to test for sex-specific effects were significantly more likely to find them. And to me, this shows that we might be biased toward finding sex differences. So when I talk to my colleagues about testing for interactions, what they usually say is that they're not powered to do that. And it's true, right? Testing for interactions requires a lot of power and therefore a lot of animals. And if you aren't doubling your sample size, you might not be powered to test for interactions. So coming back to this slide, let's say that you would normally have 16 animals of the same sex in your control group and in your treatment group. Now under SABV, you might have just 8 of each sex, which means that you might not be powered to detect your effective treatment within each sex. You would have to pool the sexes together in order to detect your effect. So let's say that in your study, the males and females respond in an identical way. Let's just say that was the sort of the real outcome of your study, that there's no sex difference in the response. And you're trying to detect that statistically. The odds that you're going to find a result like this, meaning a p-value of below alpha in one sex and above in the other, depends on your power. And if you're 75% powered within each sex to detect the effect that is there, you'll get this result 37% of the time. And if you're 50% powered, you'll get this result about half the time. In other words, if each arm, the male arm and the female arm, have 50% power to detect the effect, then this analysis approach is equivalent to flipping a coin 2 times and then declaring a difference if they don't land on the same side. So coming back to this reviewer guidance for a second, NIH does not require a doubling of sample sizes or for studies to be powered to detect sex differences. And I wanted to call your attention to the fine print here, which addresses power specifically. So it advises researchers to analyze and publish sex-based data, even in the absence of power to detect sex differences. And this would permit the consideration of the influence of sex. Now, I think the reason for this recommendation is that so that the data can be used by future researchers to do things like meta-analyses, which of course makes a lot of sense. This guidance could also be interpreted to mean that it's okay to test for effects within each sex, which would predispose researchers to make the DINS error. So I recommend always testing for an interaction, even if you don't think you're powered to do that. And if you do find one, then you have some evidence that the males and females responded differently. And then you could test for effects of treatment within each sex. You just want to be careful not to accept the null if one of your p-values is higher than alpha. Now, if you don't find an interaction, then you don't want to test for effects of treatment within each sex. You would just say that you have no evidence that the males and females responded differently, with the caveat that your study was not powered to test for sex differences. And then, of course, it's always a good idea to report effect sizes, particularly if you're underpowered, and to publish your raw data disaggregated by sex so that they can be used by other researchers in meta-analyses. Okay, so now let's say that we have detected a sex difference using rigorous statistical approaches. How do we know that it is an important sex difference, one that could end up affecting health outcomes? How do we know that it's clinically relevant? Here's a slide from some NIH training materials listing a few reasons why SABV is important. And this top one, that men and women react to many drugs differently, is number one on their list for a reason. This is the most cited rationale that I've seen for SABV. So let's take a look at what we mean by differently. What does that typically mean in practice? And to ask this question, I'm going to be pulling from this paper that came out in 2016. And you'll see some figures that I made with the companion website, which is called sexdifference.org. And on this site, you can enter the mean and standard deviation or the standard error for any sex difference that you're reading about, or sex differences from your own work. And it'll plot the effect size and the degree of overlap, assuming a normal distribution. And then for other kinds of differences, or if you just don't like pink and blue, and I would understand that, you can head to effectsize.science, which does exactly the same thing, just with different colors. Okay, so getting back to the word differently, what does this mean? So what I'm showing you here are fake data on clearance of a fake drug that I'm calling dimorphinil. And here are the raw data. And then down here, we have the distributions drawn with sexdifference.org, and our p-value is 0.01. So this is a significant difference. And Cohen's D here, this is the effect size, and it's 0.6, which is a medium size effect. And anything above about 0.5, we do want to pay attention to as potentially important. And I'm quoting Sabra Klein here. Many of you may know her. She's a well-respected leader in the area of sex differences research. So we have here all the makings of a significant sex difference that could be clinically important. But let's look more closely at the raw data. We can see that despite all of these numbers, there's about the same number of men and women above and below the mean, which is shown here by the dotted line. So we have 22 men and 18 women above the mean, and 22 women and 18 men below the mean. And the vast majority fall into the same range, and the sexes overlap by 76% based on Weissman's delta, which is a measure of the extent of overlap. So this is what we mean when we say men and women metabolize the drug differently. And to speak to the title of my talk, this is what we mean by a sex difference. Sex explains some of the variation. But what I want to point out is that you can't predict anybody's clearance rate from these numbers just from knowing their sex. So if you know somebody's sex, your guess about their clearance rate would be not much better than chance, and the other way around. If you know their clearance rate, you can't guess their sex, even though the p-value is low and the effect size is compelling. Now, you can also use sexdifference.org to make graphs like these, where you can see how many males fall above or below the female mean and vice versa. And in this example, 28% of the men are below the female mean, and 27% of the women are above the male mean. So if we were to give sex-specific dosing of dimorphinil, a lot of people might get the wrong dose. So these purple men might be overdosing, and these purple women might not get enough. But like I said, this is a fake drug, so let's look at a real one. Now, this is the flagship example of the need for sex-specific dosing for pharmaceuticals. Zolpidem is a treatment for insomnia, and it's marketed under the brand name Ambien. Back in 2013, the FDA announced that women should not take a full dose of zolpidem because they're at greater risk of excessive side effects. And one of the people studying this drug is David Greenblatt, who actually disagrees with the FDA recommendation. And he published a paper about it in 2019, and that's the title that I'm showing here. Now, Greenblatt and his colleagues argued that there isn't a good rationale for the lower dose in women. And they point out that no other regulatory agency in the world, other than the FDA, has recommended sex-dependent dosing. And one of their major points was that underdosing women could have important consequences. So here are some data from a 1995 study that was done entirely on women. And what we're looking at are the distributions of the effect of placebo versus zolpidem on driving impairment, which is here measured by how much weaving a driver is doing during a driving test. And higher scores mean more impairment. And we can barely see the difference between zolpidem, which is the green curve, and the placebo, which is the blue, because they're overlapping by 96%, and that's the striped area. And we compare that to this result. So here we're comparing placebo to partial sleep deprivation, which is similar to what someone with insomnia would experience if they couldn't get zolpidem, or maybe they were underdosed. And so sleep deprivation has a much larger effect on driving performance than the full man dose of zolpidem. And again, this study was done entirely on women. So Greenblatt's group is concerned about underdosing because inadequately treated insomnia could in fact be more hazardous than zolpidem. I just want to finish by showing this cartoon that I recently saw at a talk about SABV. And it really got me thinking about what we mean by equity in healthcare. Now, if we apply the message in this cartoon to the zolpidem case, then equality is when everybody has access to the full dose. But under equity, women have access to only half the dose. And here I've plotted the most recent data on plasma concentration. So this is from Greenblatt et al., and it shows the area under the curve for the full dose of zolpidem over 8 hours. And the FDA argument is that women have, on average, higher plasma concentrations, so many women are overdosing. But if you take these numbers and take them to sexdifference.org and look at these graphs, 21% of men have higher levels than the average woman. So if the average woman is overdosing, 1 in 5 men are also overdosing. And then 32% of women are clearing this drug like a boss, and they don't need the half dose. But women can't get the full dose in this country unless it is prescribed off-label. So my point here is that even when there are substantial, real, significant sex differences, sex doesn't always explain a huge amount of variation. The variation is likely to be explained by something else. So obviously nobody's going to go have their plasma levels of zolpidem measured in order to know what dosage they need, but at least part of the clearance rate for that drug is explained by body weight, which is available to prescribing physicians. So maybe there are better markers of clearance than sex, and we should always be using the best markers that we have access to. Which brings me back to how sex is operationalized. So here in this cartoon with the stools, sex is being operationalized by height. And if we were to give each person a stool according to their height and not their sex, then we can have equity. So when we make decisions based on sex as a category, we might miss out on opportunities to develop treatments that would target sources of variation more accurately. So we need to keep our sights focused beyond sex when we find a sex difference, to look further, no matter how we define sex, whether it's hormones or height or gendered occupational exposure or whatever, and ask ourselves, what is the true underlying cause of what we are detecting as a sex difference? Because the cause of a sex difference is never going to be simply sex, because sex is a proxy for many different things. So overall, my take home here is that, of course, we need to include all genders and sexes in our studies, but at the same time, we need to hold ourselves to high standards when it comes to detecting and reporting sex differences. And we need to be careful about adopting binary approaches to healthcare that may leave out huge numbers of people who don't conform to sex or gender norms with respect to their biology. Now, I want to thank some of the people who have inspired me and supported me. Peg McCarthy, who got me started down this road, Evan Good, who developed sexdifference.org, Katrina Carcasis, who's my collaborator on that interview project, which is funded by Emory SCORE, a specialized center of research excellence on sex differences, and you have a SCORE at the Brigham associated with ROSA. Yesenia, who helped me with the paper on the DINS error, although at the time we didn't know it had a name. That name came from my colleagues, Colby Borland and Andrew Brown, who are at Indiana. And I'm currently collaborating with them to look at the extent to which the DINS error is leading to the wrong conclusions in sex difference research. In other words, the extent to which positive or negative findings might be overturned with a better analysis. So stay tuned for that. And then I want to thank the Neurogenderings Network. They're a group of feminist neuroscientists and scholars who really hold people's feet to the fire when it comes to sex differences research. And thanks again to all of you for giving me this opportunity to kick off the symposium. And I'm really looking forward to the rest of the talks.